Well, I think we have a quorum now, so let's get started. My name is Tom Blank. I'm from Microsoft Research. I'm a program manager, and I'd like to welcome you to the Microsoft Research Cooltalks. First, a small commercial, won't take long. The basic idea of Cooltalks is to tell you about the technologies that are going on inside of Microsoft Research. In research, we will have failed if we basically don't transfer the technologies out into the product groups, and so we're always looking for ways that we can get the information out to you guys who are actually building the products and shipping them out to the customers. So one of the ways we do that is with Cooltalks, and so every other week we have a Cooltalk. So in 2 weeks, the next Cooltalk will be a gentleman by the name of Michael Friedman. He is a world-renowned expert in quantum computing, and so he'll be talking about how basically quantum computers work. But come to that if you can. Other methods that we try and transfer technology is through, for example, the MSR web page. And so this is a web page that's available to you. Up in the upper right-hand corner, for example, if you type in this web page, you'll see a picture of a face of a program manager, one of my colleagues, who, for example, his assignment is to help facilitate technology transfer into your particular product group. So if you can find what you need just by looking on the web page, go for it. If you want to talk to somebody who can help you get connected with, hyperbolic transporter banners or whatever it is you're looking for, you go ahead and do that too. Any way we can help get the technology out is the right thing to do. So please ask questions, send emails, smoke signals, fax, whatever works for you. Anyhow, without further ado then, let me introduce Hoi Vo. He is from our PPRC group. They have built some of the incredible tools that we're using in production today to ship Windows and many other products, and some of the technology they have is actually going to be shipped in the next version of Studio. So without further ado, Hoi Vo.
Hello everybody, can you hear me okay? My voice is kind of low after the winter, so please bear with me. So today we talk about BBT for mixed mode. BBT is nothing new if you've been in the process of to do post-link optimizations for Windows or Office, SQL. The part of we started out with mixed mode binaries because we have a new breed of binaries being shown up. It was not a predominant factor in the past, but now we get to think about mixed mode in a more serious way because the interoperability between native code and managed code is becoming increasingly more important for the company. So when we started out with this project is basically, it was born from the fact that we started having mixed mode binary where you have MSIL code together with and native code together in the same container of PE binary. So now how do we do this thing? The current BBT binary only works on native mode. And there is BBT process for engine portion and for MSIL produced binaries. But when you fuse the two together, there has to be some way to collaborate the two efforts together to make sure things are still making sense in the future. So to start, just introduction of what our team is all about. So anybody who has to know about the binary technology team, you can get an idea of what we are about. The background of BBT. The current process we're going through with native code, what is the mixed mode twist throw in the frame? How does instrumentation optimization will work in the future? And then we'll talk about the future with Phoenix, because that's what we're focusing on right now if we don't have the mixed mode bandwagon coming in the middle. So anyway, part of the binary technology team, the last time we talked about is Nirvana, which is the second bullet. So this time about BBT for mixed mode, which is the first part of it. We look at Windows as a platform, so anything that runs on Windows should behave and will perform well as well. So for that purpose, we built a set of tools that kind of take Windows code to run better on Windows, make sure they beat Linux and any other advantage we can get out of that. So our goal is basically continuously improving the Windows platform. So a short introduction is BBT is post-link optimization toolset. So if you have not played with BBT yet, because BBT mostly runs at the build lab, and a small team in a large organization usually taking care of the process for you, so you don't have to worry about it. It's more like a push-button kind of thing where you you produce your binaries, and then BBT just take the binaries and instrument the binary, run through the scenario, and then produce the optimized binary, and then that's what you can run tests on. So when the build comes out, there's a post-build stage where BBT is part of. And that's where we take advantage of the fact we come in right before you ship the binaries and take advantage of all the binary we can see right there. So we do instrumentation at the binary level. We do profile-guided transformation on the code itself. So right now, the major transformation that we do is about code layout to fit better in the cache, to fit better within the level 2 cache and level 3 cache as you have larger binaries. And from there, we can go down to the microarchitecture of the CPU itself, where we do cache align things. And then we just go down the memory hierarchy as we go. And then we use profile information to do the transformation itself. And as the 3 bullet in the profile guided transformation right there, you can see that basically we build an internal representation of the binary, fill it with the profile data, and then figure out what is the best way to lay out the code. And we handle both static code as well as static data blocks. Static data blocks means resources, read and write data, read-only data, that kind of stuff. So we move it closer to the code to reference them, or we put them together in the right phase so that when you touch a certain piece of code or piece of data, most of the thing that it needs probably falls approximately near the location where that block is. So does anybody know what the basic block is? Okay, I'll go through that later on. So the memory hierarchy performance is basically when you first run on a machine, before you even get to the CPU, you got to feed the data off the disk. So as you go down, the disk and then the cache and then the CPU cache and then everything else, that's the memory hierarchy we use to leverage from the BBT toolset. We take advantage of that to make sure that we basically don't have to page at all if we don't have to, and then we go down to the cache misses and everything else. Because every time you hit the disk I/O, it's really bad. So in terms of code optimization, what kind of things do? We do code placement. So we use temporal information to find out when the basic block gets hit. Basically, basic block of code has been single entry, single exit. That means you have only one way to exit the block once you enter it. So that's how we define the basic block. So we break up the program code into a bunch of basic blocks, and that's how we move things around. And that's how we attach profile data on top of the basic block as well. So the classic code optimization we do is control flow restructuring, so that way you don't have to take a jump if you don't have to. Code specialization, so when you have an indirect call, like a virtual call from one place to another, how do we make sure that you don't have to have a cache miss if you can afford to? So if you take a virtual call too many times, we do specialization to move the method closer to the place where the invocation is happening. And then partial inlining, so basically we can take if function A is inline, try to inline function B. Part of function B is live only, which is basically touched by the scenario that we care about. We don't have to inline the whole thing. We inline just part of it. So of course, the inlining we do here is very rudimentary compared to what the compiler is doing. That's why we want to work on Phoenix, because the gain is the compiler is doing all these flattening of these registers and also the calling conventions where the best gain is coming from. We only move the code close to the other one. So that's what happened in inlining BBT right now. So the basic block layout, to give you an idea what we do, so this is not how the code is laying out, by the way. It's not like a binary tree. I just give you a representation of what it is. So when you write code, you have no idea which function is located next to what. So basically, usually, when you write code, that's how things are laid out in memory. So you can write code, and then, okay, I call this function, I define this function, and write the code inside of it. And then that's because it's your source file. And then when the compiler and linker put things together, that's basically how things are related to each other in some way when you look at the functionality for a certain feature. When BBT comes on in, and we see that basically if you have a certain way, let's say that you do breadth first search, for example, breadth first operation through the control flow of the program. So you're going to have to basically, the preferred locality for the program is this way, which means all the functions at the same level would like to be packed together. And that's what BBT does for you automatically using profile data. So the control flow restructuring, I'm trying to visualize this a little bit more accurate for you so you can see actually what is going on inside of the function itself. So the previous slide is about functions level. So you can move things at the function level. So this slide gives you what happens within a function itself. When you start opening up a function, you have a control flow in there where you have loops, you can have branches and stuff like that. So when BBT instrument the binary, basically it tried to look for how often do you go through a certain path. And then based on that, so the right-hand side is basically, let's say that's the layout of the blocks in the function in the original format. So you write A, B, C, D. That's how your mind works, right? So we write the code in that sense. And then when we have profile data, we see that ABD is a predominant path, and ACD is take place only one, because there's a loop on the other side. So it's best if we lay out ABD and then C. So that happens automatically with BBT. So it reversed the branch for you. So basically, it maintains the control flow as you go through it. And it retains the control flow, so your code doesn't behave any differently. But the place of the blocks are suddenly now moved. So when the CPU is executing the code right there, the cache is feeling much better, because now you can see that you don't have to have a cache miss when you execute the loop to the loop most of the time. So regarding the data optimizations, so right now, everything that we talked about so far is happening on the native side, which is the part that we want to do for mixed mode on the native side as well. So data optimization, what we want to do is we want to make sure the layout of the data in the data sections. If it was read-only, we preferably move to the code section so we can put it next to the code to reference the data. If it was data in the data sections, we try to co-locate them together, so that way when you access the descriptor for function A and the descriptor function B, or the data for function B located next to it, and A and B is appropriately execute together, then we want data for A and B to be located together in that particular section as well. If you're not familiar with the section is basically a smaller container in the PE hierarchy of the binary that you execute. Section basically composed of many different clumps of data or code within the binary itself. So right now, static data is basically like go from vtable to const integer that you declare in your program. And then that's read-only, or you can declare just integer, which is read and write data. And then resource are basically .resource sections. Right now, the resource sections we're not doing as good, because we're still running using the granularity of the resource loading API. And sometimes most of the app that we know load a bunch of resources and access them separately. And therefore, we don't see the reference that happened underneath. So you still have a lot of paging out of resources, especially in the Office applications. We still haven't done a great job there. We still figure out what the best way to do that. And hopefully with Nirvana, we can get the answer, because now we can get the profile data that was necessary for us to move those blocks close together and recompute the directory for the resource directory correctly. Yes?
That the repositioning of those basic blocks
Yes.
happens on the fly.
That happens, well, we take in the binary, we reshuffle them, and then we write out a new binary.
But
I'm sorry, the question is, are the reordering happen on the fly? So all these things are static transformations. So we read in the binary.
But for example, that control flow graph that you showed, the packet, the path ABD is the most frequently traversed path.
Yes.
You may not be able to determine that until you actually execute that CSV, right?
Correct. We profile the code, so we know in advance what it would look like. So I will go through the process. You can see exactly what happened. So the question is basically, do we reorder things on the fly when the program is executing? The answer is no. BBT is a static post-link optimization tool. The other one is completely different, where the JIT is doing more things on the fly. But that's not the environment that we're talking about here. So let me go through the current BBT process so you can see what I'm talking about in a high-level sense. With BBT, we take in the PE binary, which is the binary that got produced off the build lab. And then we go through an instrumentation process called basic block instrumentation. So that's the name of the program itself. So it instruments every basic block for the data that we care. And then it writes out a new binary, new instrumented binary. And from that, you can run your favorite scenarios. So you go through, you can run for Office, for example, you can load a document into Word and then copy and paste into Excel or something like that. And then during the process of instrumentation, you create an IDF file, instrumentation data file. And then from there, it feeds it through BBOp, which is the optimizer, and then write out the optimized binary. Most of the time in the build lab, in reality, nobody has time to go through this step. The reason is because it takes quite a while for the build to be done. Nobody wants to sit around and wait for the thing to go through instrumentation, run scenario, something might breaks down, BBT didn't work or something like that. So most of the time, the main build lab, Windows for example, with almost 300 binaries that you go through with BBT process, nobody has time to wait around. So we wrote a tool called BB Incremental, which takes an old optimized binary or old profile data from the previous time you run, and then incrementally propagate to the new binary, and then we optimize it. So this one saves quite a bit of time, because as long as we are good at the differing engine, which is the last Cooltalk where one from our team with Zhang Wang did it, we take two binary, figure out what is different between the two, and then accurately propagate the data, profile data from one side to the other side. And then that way you can have the new profile data for the new binary without even going through the scenario. So that's how we basically capture the profile data without being offline. So that way you can have the main build process going through without any churn. And that has been the most favorite way people have been using it. Although that with the control flow structuring that we're talking about, it requires very accurate profile data. And most of the time, if the stale profile data is coming from a binary has been changed quite a bit, this process breaks down. So that's why the way NT does it, they do the instrumentation of the build, private build, the day before the main lab does that, and keep on propagating it. So that way they're very close to the binary that was going to be shipping, but the instrumentation doesn't have the tech effect, the main build lab doesn't have to worry about instrumentation. So that's the process they go through at this point. So that's where we are with BBT for native code. Now we go on to mixed mode. So that's a whole bunch of twists we're going to throw in. So mixed mode binary is a PE just like usual, but inside of it it's going to be quite different. We have native code, MSIL, and metadata together in the same binary. MSIL code is what you produce with C# usually. But if you write managed C++, you get a bunch of native code inside of it. Or you can control the compiler to have certain functions to be emitted as native, a certain function to be emitted as MSIL. And then the metadata accompanies the MSIL stuff. So you have the type informations, you have all the strings, you define all the mapping, all the everything you want to know about the MSIL code is in the metadata itself, which is, we love to have that, because for the native code as well, we never rarely have to the same equivalent kind of information. The only thing we have is PDB information, which is sufficient to do layout kind of things, but not doing the type of compiler optimizations. So with this kind of settings, what are the active BBT can do right now? Most of the time we can do is basically, the goal that we trying to get to is basically optimize the native code, leave the MSIL code alone, so that the process of BBT for MSIL would take into effect, and then also reorder the metadata as well. Because now that we're looking at, we got page fault in 3 categories in the binary, not just native code and static data as usual. So also the fact that basically we have transition between native code and MSIL code that we want to capture as well. Because this can tell us if we're calling managed code transitions too many times, or we can basically, the transition here is costly, so we want to make sure that the transition is necessary or not. Depends on the information we get from the profile data. So it's very important for us to figure out those things out as well. We can always do the native code right now, which is where the state where we are right now. But we want to take the extra step. We'll make sure the process is going to be easier enough for everybody to apply it in their build process. And right now, even the BBT for MSIL code and BBT for native code, right now it's very costly. And I'll go through the details a little bit more, what we can do to improve the process. Because mainly, if the process breaks down, no matter what the tool can do and how good it is, it's no good for anybody. So, any questions so far? Yes. You jumped right into the killer questions. The question is, can I delay that until later on? Because I will talk about the schedule for BBT for mixed mode later on. So everybody will be killing me at the end if they want to. So, I'm sorry. The question is, does collecting profile data induce more overhead for other things that might cause different behavior?
You run a certain set of steps.
Yes.
Like this is the common usage.
Right.
And then you arrange all of the binaries.
Okay.
That's
correct.
That particular process.
Oh, okay. So if it runs through a different scenario. Okay, so the question, if the binary has been profiled a certain way, now it applied to different situations, what will happen? Those path is going to be the more expensive path now, because you're going to be killing the caches. You're going to be jump all over the place to execute that. That is very undesirable. So that's why it's very important to get the right scenario for your application. So that's why Office has 2 gigabytes of profile data that they want to process, because you want to make sure you cover the most basic cases that somebody might use the software. So you're right. I mean, getting the right profile scenarios is the most important thing in BBT process.
And are all the scenarios
Yes, everything is automated except for the scenario, because the scenario is very customized based on the application set that was running. So everything is automated except for the running the scenario itself. Yeah. Right, that has to be based on the application that you're profiling.
But once you determine what the scenario is for that application, then you automate that.
Okay, so I'm sorry. The question is, once you determine what the scenario for your application, can you automate that? Of course, like Office using visual tests to drive things, for example, or they have this suite test called Oasis to drive things automatically once you have done with it. Yes. Yes, you can prioritize the scenarios. If you look at the documentation for BBT, you can have phase within scenario as well. So you can have boot up, you can have print a document, you can have graph document, you can have many different phases. You can prioritize them, and you can select even a layout strategy for each phase itself. Okay?
Do you have a feedback way of getting profiling? But even if I run it in a new scenario where it's performing badly, the feedback generated from that scenario can be used to generate.
Yes, I will go through that in more detail, because that is the killer part for most group. The question is basically, how can you feedback the data if you have another scenario you care about? How do you know when things go not right? Basically, we have measurements to give you that feedback. Yes, I'm sorry.
Are there any guidelines for how long the scenario will be used? Because I know in Office, we always say whether you're running on scenarios on like individual actions, such as opening a document versus going through a long scenario, opening many documents, taking them, things like that. Are there any recommendations for that?
The question is how long the scenarios have to be, and can we have a guideline to say how do you put together scenarios together so you can have a best bet of the both worlds? The answer is determined through the validation that you have. There's no way you can say that any scenario is going to be dominant over some other scenarios until you do some validation to say, is the working set affected by including this particular scenario that can cause crazy ramifications over the past scenarios you have. The only way to find out is run the workset tool that we have to visualize before and after when you add a new scenario to the array.
That works now. I do that, but I was just wondering if generally if you had the same operation, like you open a document, if you open a document and then save it, have it in one scenario versus breaking it out into one scenario that opens, one that saves, and having to specify the rest of it now, whether there's any general rules.
Okay. The question is, how do I know which operations how to best stitch together the operation in the application to make up a good scenarios? For example, open a document or print a document. Make sure the open document is one scenario, print a document is another scenario, or you just put them together as one scenario. For BBT, it really doesn't matter. The reason is because we look at the whole if you put together those things in one phase, we look at the whole thing. And how does that affect the whole binary? Not a particular code path only. Because we look at temporal profile data, so anything that was executed together, that's what we're looking for, the characteristics of the program inside of it. How does it execute together? How these methods, functions execute together. That's what we're looking for. Not necessarily exact. We don't know what open a file is. We only know when you have these scenarios together, that's what these things execute together. So if you think these operations should be done and concurrently, that's what you make up your scenarios. Or sequentially, that's why you make up your scenarios. Yes?
So to sum it up, are you saying that your tool does a certain job, but we still have to determine how to put the scenarios together?
Correct.
To the right information?
Correct. The scenario is very important because you know you are the best person who knows about the application. So I want to emphasize again, if the scenario is wrong, BBT will do the wrong thing. And then when it goes out there, it's going to do really bad. For example, we have a case where one particular scenario, I don't want to mention the application because confidentiality, but we forgot one of the most common operations because most of the tests are automated. So when you ship something like that out there and people start using it in the regular way, it starts execute really slow. We don't know exactly what happens in the last drop or this drop. But apparently we finally figured out that one of the scenarios was never run. So you can see the implication. We had to actually reissue a service pack for that particular app for that. So, okay, so let me go on. So beside all of this stuff in the PE, we have the dynamic side, which is the heap as well. So if you look at the whole working set that was put together by the mixed mode binary you run in the managed environment, you have all these things playing together against each other as well. When you use the heap too much, you access the MSIL stuff, or you engine the binary, you still have to access the metadata, or whatever it is that you have to do. These things play against each other. So we have to basically have the right measurements to go forward, have the optimizations span from end to end, and not just one part of it. So right now, BBT just touch a native code. That's not enough. So the challenge with mixed mode, the instrumentation side, we have to build the right internal representation that can show the control flow, the transition between managed code and native code, and instrument all those points as well. So right now, we have managed entry point to go from native to managed code, and the P invoke, the platform invoke, to go from managed code to back to native. But the platform invoke inside of a mixed mode binary is much cheaper than the other one, when you go across module completely. But still, you have to figure out a way to figure out all these imports and instrument all these guys together to make sure that you can have a good view of what the program is all about. And the second thing is metadata access. Right now, the only thing they can give us detailed information about about metadata access is Zapmon, which is a utility from the CR team. They did a bang-up job to get that information out. But it's huge data, and then it's also, the data collection is quite cumbersome for the build lab to do. So that way, I'm not sure how somebody else might have a huge app can put together all these things again, or know exactly what are the steps to do. The process is basically quite cumbersome right now. So on the optimization part of it, native managed code are mixed together. So what we can do right now is we move the IL method, even though the BBT cannot do anything at the IL level. It will move the IL method close to the right place, approximately in the file. So if you have to run through the JIT process, the paging behavior out of that is just normal because you still access the IL before you can JIT it. If you engine it, that's great because now you can have all these native methods, semi-native and actually native, mixed together in the right set, in the right co-located together correctly for that particular scenario that you have in mind. We don't split the managed code IL. Ngen is the only process that can do that. Metadata reordering also is a post-link step for the MSIL side as well. Incremental. Incremental will happen for native code just like the same way. So you don't have to change anything. But if you have a method that switch from managed to become native or native to become managed, we don't know that. And also, when we already have an IL diffing, so you can have, if you have a method in IL that changes, how do we map them up together? Right now it's quite hard because the signature is no longer the same. If you change the parameters, the metadata is also the place where we look for things that were different. So diffing at managed code raised the level, complexity one more levels for us to be able to look into it as well. So when you propagate data from the old build to the new build, we have issues along the line where if you change something in the metadata, in the IL code, where we can no longer ascertain the similarity between the two. So those are the challenges we have in mixed mode. So let me go through the BBT for MSIL path right now so you can see what are you going through when you do BBT for pure C# binary. So one path is where we put up together because we believe in steady state working set, which is basically once your app starts running already, there is a affinity between the method that you want to have other than startup. So BBT can do very well at the steady state level, but for startup, it's almost lay out things sequentially. We can do that as well, but it hurts the steady state one. So we have to be some way to compensate for the two to exist together. So right now, BBT for MSIL, we take advantage from the fact of the profiler mechanism hooking from the CLR. So you no longer have to instrument the binary. You just tell the system you want to instrument, and then everything will just, the data collection will just happen automatically for you. Except the fact that you have to clean up the system. You don't have anything engine. It has to go through the JIT, stuff like that. So after you run it, you have a bunch of IDF files, and you create it through BBOp, and you create an IBC file. The IBC file is short for instrumentation block count. That's what we come up with the CLR team in the JIT to do the code separation. And that stays there. So let's stop there for 1 second. So now, if you want to go it from the NGen phase, you can go to the PE, which is the mixed mode binary or MSIO binary right now. Go to NGen/instrument. It produces a new NGen binary, which is basically instrumented, and then you can install that GAC correctly in the right place, and then you can run your scenario, and you create a bunch of IBC files. These two are merged together. The IBC files that we produce from BBT, from BBOpt, is only the relative order of the methods. The IBC file provided by the PE, instrumented through NGen, has block count inside of it. So the two merge together, and then you write out a PE-opt, and then you can go through the NGen process. I'm sorry, the wrong thing. The IBC merge is only produced a new PE-opt, which is MSIL still. The resource section now contains the data that was necessary for NGen to produce the pre-JIT PE. So that's where we are. So you can see that the steps is so many steps to go through. And I'm not sure I can keep it straight either. So I'm working on the team. So basically, we have many people keep on refining the process. And we hope to someday where Phoenix come into play. Phoenix, I will talk about it later on during the talk. When Phoenix come into play, everything would just happen normally. So that way you can say, I want to instrument the code. It doesn't matter what code it comes from or whatever it is. It just works normally. Right now we have to jump through many hoops, too many processes to go through, and so many ways to error. Yes, questions? BBT doesn't work for the NGen binary, if that's what you're trying to do. The question is basically if you can push through NGen, optimize through NGen, convert to a native applications, and then push it through BBT. The kicker part in this thing is the pre-JIT PE, the format, is quite confidential. If not confidential, it could change with time. So the BBT process had to follow through with it to be able to do the right thing. But on top of that, NGen happens on the client machine. You don't want BBT running on the client machine either. So the process breaks down right there too. Everything has to happen in NGen if we want to have it done right. Yes?
So currently, what's the timeline looking for build out
How long this process would take? The mileage will vary. I can hardly give you that feedback. Given the number of steps you have to go through, even us know that it's going to take longer. So it definitely takes longer than native just because you have to go through many more steps. The native side, the most expensive one is running scenarios. In this managed code mix, we have much more things to worry about than just collecting data. Collecting data is one aspect of it, but you have more things to worry about. Where do you put the binaries? How do you run? How do you validate it? How do you put it in a situation where you can validate this thing? Because you have to go through the post-NGen process to understand exactly how your application will perform on the other end. The incremental will happen at Microsoft, hopefully. So that when you run NGen, basically that last part is happening on the client machine. So you don't have to worry about it at the client. But on the decision that was made, which function, which method to put close to which, and what do you need to do within the binary and what not, all those decisions should happen already in the binary that we ship out. And NGen just follow those hints to get things done. Yes, Chris.
Reasons for going through the CLR profiling APIs instead of doing something like managed instrumentation of the MSIL.
Okay.
What's happening with that?
Okay. The reason I go through that top box is to explain the current situation for BBT for MSIL. For mixed mode, you have to go instrumentation. You don't have any choice because of the native part of it. The native code, you don't have any way to call back to say what code get executed, what method get jittered, or however you want to see these things. And also on the top one, you don't have any profile counts for basic blocks. You just know when a method gets loaded or not. And that's what BBT does best. It basically knows how to put the relative order of these methods together. And then the lower part we take care of within the function. So how do you separate the code out? How do you move? How do you take out the not so common path and move it out, so that way you can have packed densities within the cache, for example. So the two of them kind of play together. You can use one without the other. Right now, if you just care about code separation, you just run the lowered part. If you care about the steady state, you can run the top part to compensate the information to the engine later on to do the right thing. So right now, the process basically is broken into two like that. The reason I mentioned that so that you can see the complexity of the BBT process right now versus what I showed in the beginning. It's just instrument, run, and then write out a new binary. It's just one step. But this requires more things to be in place because of the dynamic compilation nature of the JIT itself, the CLR. Is there any other questions? Okay. So let me move on to current state. So right now, it's not very smooth. You can see this. Basically, you can run through many steps to get things done, and too many ways to error, even for us. If we have to sit down and instrument MS core lib and try to optimize MS core lib just to see what's going on, we get killed by it as well because so many ways that you can mess up the process. Where do you put the instrument binary? Where do you run these things? Is it in the global application cache? Is it in a native assembly? Where is that you want to put these things? The current optimization impact is limited to IO image only. And no common methodology for validation things. We think of a certain way of looking at binary when you run it. Other people have different measurements. We don't have any common set of things you can say, yes, it does better because of this. Everybody has their own view of it. And we don't know quite how to remedy the situations right now. And the team needs are way too different. Some people want to do IL, one people to do an engine. Some people don't want to deal with the steady stage. Some people just do startup. How do we want to do this thing? So many flavors of this thing to cause a problem. So where do we start? So the thing is basically with BBT for mixed mode. So let's look at the function. Right now, this function is both native or managed code. You can see it. So the first thing we do is temporal information. So we capture information that once you execute a certain basic block, and we're recording when those methods are being executed. So that happens no matter what. And we do this per basic block. So it happens for everything inside of the native binary as well as managed code. For managed code right now, we do that for the top level function entry only. We don't do that for every individual basic block because we cannot move them anyway. We want to do that for every basic block only because we want to know more information about how this function is going to be executed versus other methods. So if you have a loop inside of it, spend a long time inside of it, we get more information out of temporal information than just the entry point. So that's why we want to do it at basic block level. For the block count, the reason we want to do the block count is because when you return from an external function, let's say f belongs to a function somewhere else, not in the same function. When you return from the other functions, when you make a call and you return, if you don't instrument there, we may lose some cohesiveness within the control flow graph in terms of how to attribute the profile data to individual code path. So we need to do that one there. And then the edge flow is for looping, for example, so you can see how many times you execute in a loop versus the edge that goes through. For example, A, you can say A execute 10 times, but 9 times come from the loop and 1 time from the entry point. We need to be able to discern that. So indirect flow is basically when you call from C to F, we don't know where it's going to go. So we want to make sure that we can instrument the source and then the destination so we can see exactly where things are going. And then we can pair them up later on. So those are the basic instrumentation that we do in the mixed mode binary, just like native. The optimization that we do, the native code, no change. We do everything that we BBT should have done, which is separate the code, moving dead code away, packing things, make sure that all the methods and basic blocks are put together in the right locations. And then for managed code, we want to function at the IO level, method level only. So we move the whole method closer to the native code if we need to. And then using the native and managed transition, we can report back to see that you transition way too much from one side to the other. So that's what we want to do. and the IP invoke, which is a mechanism to go from native transition to manage. So,
all you do there is let people know that's happening.
yes.
You can't have sort of
We cannot restructure that because the compiler is the only one that can do that. With Phoenix, we can deal with that. But we cannot convert a method from native to manage or stop things from going to manage completely or whatever, however you want to flow. BBT is guaranteed we don't change the control flow of the program. So the last bullet, you're right. It's just more informational right now for us to figure out, to help the developer figure out, okay, this is something that you don't want to do, or he didn't realize that he's calling it across the transition so many times. So there's a routine called hresolve from Win32, and there's no need to have the transition over to the managed side to call that all the time. You can have a copy from native, a copy from managed, and everybody just go there and call it in returns, for example. So there are things hidden in the code that people don't realize, that's all. So the BB incur process doesn't change for the native side. For the mixed mode, we have to worry about the change, like we said about the IL stuff. So if you have changes the IL methods, if you don't change the signature, we can do it fine. But if we change the signature, it will be harder for us to figure out which one is the same, because you could have a method, same name, with a different parameters. And that's two different methods in the same class. Versus, how do you know when the same one has been changed from an integer to a pointer, for example, in the new application. So for the native part of it, you can pull in an old optimized binary. We just reshuffle the native part to mimic exactly the layout of the old optimized binary as well. So we no longer even need the profile data for that matter. So there's two ways you can do it. We propagate the profile data and let the optimization process as usual, or we mimic the layout. So we should take whatever the old optimized binary, we reshuffle to look exactly like the old optimized binary. We don't even need profiling. We just go blind faith. So that's the two incremental process that we have at this point. So some preliminary results you can see. This is for System Windows Explorer.dll. You can see that the gain that we have from BBT is not that much. But I will break it down a little bit for you to see, to understand why. So right now, BBT is usually saved up about 50% of working set. And this is just on the text section alone. But if we break it down, the thing is basically we optimize the native portion, the IL portions, and also the metadata is also inside the same text section right now. So it's not bad where it is. I just mentioned that basically the fact that we have a lot of page inside of it, so the gain you see is not as much. But if we break it down to remove all the metadata into a section by itself, so that way we can quantify things better. So now you can look at the patient behavior. You can see that for code alone, we can get a lot about, you can learn to see we do about 50%, which is the ballpark of the right amount that we save. On the metadata, we don't gain anything because we're not moving anything. We're not reordering metadata right now. So the top part is metadata. The lower part is the IL and the native code that got touched in the scenarios. And this is about a startup scenario. So you bring it up, you kill the Explorer, you start bringing it up again. That's what you see. So right now, the gain is about 50%, which is what we expect from the BBT optimization for layout. So right now, if you look at it, what good is a BBT right now? Because metadata is right now is hundreds of page faults. Code is only like 60 at most. And then if we optimize down to 40, yippity-doo. It's not really something that you can jump up and down and say, this is great. But the thing is basically, if the same algorithm, if can be applied to any of the metadata access or jitting or whatever, jitty code or whatever it is, you see the gain coming back from it is tremendous. So that's right now we're trying to work out a way so we can instrument and look at the Zapmon data, or we can instrument a different way to see exactly how the metadata is being accessed and go through the metadata optimization from the CRR team with the same algorithm that we do. So that way we can see at steady state how much we can gain from this. And also, once we knowledge that we can do with IL method, we can also influence the engine binary as well. So that's the path that we're going at this point. Any questions? Currently, right now, okay, the question is, can we do something at the engine binary at runtime?
Yeah. At
Yes. The question is, can we do something in the JIT so we can optimize things at runtime at the right place at the right time? Hands down, I agree with you completely. It's just not possible at this point that we can go in there and do the same kind of work that the CR team has spent years perfecting. So at this point, the only way that we can do this is with Phoenix. Code-based engineering process that we can go through to make sure that we can change the way where JIT code can go or how engine emit code or whatever that is has to be in the JIT engine. So BBT is always on the outside. So now we're trying to move BBT into Phoenix, which is basically the crux of the problem we have in task integration between the two tools. So now we can have a chance to do that. So you will be able to see how JIT will be able to influence things in the future. The CR team is doing that constantly anyway. So we're trying to catch up, and then we also work together at the time when all these things are joined up together. So future direction for BBT. I just want to go through this so you can see where we're heading. The mixed mode stuff, you can see that basically we can make a drop right now. You can use it, but the effect that you have is not going to be as much. Except when you have tons of native code, then it becomes a BBT for native issue. Then I'm not questioning that part. That part just happened normally. If you have a bunch of IO method and tiny little mixed mode native code, it's not worth to go through this at all. So we will have ways for you to at least to see, at least just dump a report out of the binary to see is it valid or is it worthwhile to go through this process. Unless we can have ways to instrument the metadata, which is a big part of the whole thing, you can go through that. So right now, System Windows Explorer.dl is a good mix. It's like 50-50. So all the comp control stuff we haven't touched yet. I don't know how to activate that stuff. So the profile that you see is just start up Explorer. It's nothing special. But if you have more profile data to activate the native code more, then you can see the BBT process will kick in a bit more. So, but going forward, what we want to do is basically decoupling instrumentation and optimization process, because that's where things break down the most. So if we have a way to give the optimizer a different way to input data, so that way you can say, I wanted to mimic this binary, I want to mimic this profile data. This is something I got from my own profiler. How do I feed it to the optimizer to do this? These are the kind of things we want to expose to everybody to do, because that's where you know your code the best. There's no way BBT knows the best. Profiling is one way that we can do, but the game's rules has changed with managed code. You can dynamically bind to anything on the fly. You can basically later on we have pitching code. So we JIT something, we throw it out, and then we JIT it back again. So how do all these things play all together? So that's the last bullet, but we're trying really hard to work out with Phoenix is the adaptive mode. When you go through JIT, how do you do the best way? I mean, we have jikes running all over the place where you say, okay, you can do adaptive compilation model. But when we look closely into jikes or whatever, how they do it, the question is basically everybody kind of narrow down the problem, the specific problem that they can do, like inlining, context-sensitive inlining, or they want to do register allocation better, something like that. But it's never been a system-wide solution. You can say, how do I deal with dynamic heaps? How do I deal with pitching code? How do I deal with native code that was working together with managed code? So all these issues kind of play together because the system now is much bigger than what we had in mind before. And the optimization, with the part that I really want to make sure that you can see is we had to expose the user control dials. One of the success with BBT is basically allows you to change things the way you want it so quickly. For example, you say, I want to lay out the read-only data sections this way. And then BBT will just do it for you. Or you just want to say, these are the labels of things you want to control. And I want BBT, don't touch it. I know it best. Do it this way. And these kind of things is what plays into the process. And the BBT part really does a good job. It's very minimal in the whole thing. The process is what kills everybody when we look into this kind of level of work that we have to do. And the level from stale profile data is a must. There's no way that anybody can have profiling and then build in the process in the same way that you have a build lab right now. We can see that with Windows. We see that in many different places. And then if you have time to do it, great. But the thing is, most of the time you would not have to be able to do everything sequentially in a loop like that and be able to get out a build-in time for everybody to play with. And also the layout engine must address everything within the binary or everything that you touch. from metadata access to static data to metadescriptor table to vtable, everything. I mean, without those things, the only thing, if you just deal with code only, there's only a minimal portion of it that you can deal with, and the effect is going to be much less than usual. So how do we deal with Phoenix? So I'm sorry. So let me answer that question. When is mixed mode BBT available? The way it is right now for native code, you can have it available by the end of January. We can have a draft for you to play around with, but it's not going to be widely released until we understand the metadata issues. How do we couple it with the dynamic heap issues, optimization that we are working on, and how do we deal with the engine binary? So those three issues we have to answer before we can say that we'll release it out to wider public usage, because there's so many unanswered questions right now. So if you just have a native binary that has a little bit of IL code, we are your best friend. But if you have a lot of IL, a little bit of native code, that's not going to be effective. So that's the caveat. So we have AMD64 drop coming out very soon. As soon as the NT pick it up, we're going to work on a mixed mode drop right away. So right now, all the work that we have done, the core part of it is done, but we still have to iron out the part where, how do you know when a binary is good for you to go through the process? How do you know how to validate results, basically? So when you go through jitter engine. So as far as Phoenix is concerned, so the bottom part is what BBT is right now. So you can see that Phoenix is basically mostly a compiler in its own sense. So you can see the OBJ, you write the OBJ, you pass through Phoenix, you get it to the PE file, where you generate PE files, which go to the BBT process. So what needs to change? The thing that we want to work on is this. We want to do the right optimization at the right place, which means things that we should never do inlining inside of BBT. That's the wrong place to do it. We should do that in the compiler. And how does the compiler do this? With profile data. So we try to move all the IDF file and mapping it back to Phoenix. You can see all these things working together. And also, by working in Phoenix, the part that we kill us the most is how to map a basic block in the binary to a blob in the IR for the Phoenix. So those things that we have to work together to make sure those things can match up. And also, when you have a new build, how do you map things back up together? And you have profiled up the previous day, and now a new build's come through. How do you map that data back? So that way the build process just goes through smoothly and produce an optimized binary, but may not be the last step you go through, but there's a choice you want to go through more steps if you want to. Right now, we don't have any choice. So the other thing is basically we have built a path to take the PE binary from Phoenix, which is a different mindset than before. Before you have an OBJ file, you compile down to IL, and then you push it through the back end. Right now, the Phoenix infrastructure can take in the binary as well. And so far with that, we can basically replace BBT completely from Vulkan, where it was residing on top before, and then do all the kind of information, using all the information that Phoenix has on the code. We can do more sophisticated transformation of the code itself. And that's the story where we look at the instrumentation. That's where we're trying to decouple the instrumentation and the optimization part of it. Instrumentation can come from many places. And you can just run LOP. You can run or your own profiling to know a certain code has to be a certain way. You can map it back to the compiler and say, these are the things I want you to optimize, and this is the information I want to give you. And the compiler should be able to take that stuff and do the work that it needs to do. So that's where we want to get into. That's the place we want to do with Phoenix. So, and then resource, any other questions you might have? Yes? Nirvana talk has some messed up, so the video, but the slide up there. Right. There is no Nirvana, unless I can go back in time. But if your team needs to, I can come by, or somebody from my team can come by and give you a talk on Nirvana.
Second question is on your binary optimization is one thing. What about actual code optimization? MSR ever looking into this or something?
Yeah, I think we have more than you can count, but the thing is, how do we make them into Phoenix? That's the point. So we do have a lot of team looking into virtual call, devirtualization of method calls. Okay.
So that what we do is make your job and get the best performance and while maintaining security.
Okay. We would love to talk to you.
That note would be probably great if you want to talk before you get we'll do stick around and come on up if you have more questions. Thank you all for coming. Can you reach Michael, please, in front of the computer?
Why, just in time.